In the last class, we started introducing a new topic called multiple quantum NMR. These multiple quantum transitions are the ones where the change in the magnetic quantum number between two energy states is anything other than plus or minus 1. It could be 0, plus or minus 2, plus or minus 3, etc. Anything other than that, other than plus or minus 1. And I also said for such a situation, if I have to see double quantum, two spins will be flipping at a time simultaneously. If you look at the single quantum, we saw only at any given instant of time, only one spin is flipping from alpha to beta or beta to alpha. Whereas for higher quantum, it is a combination of coupled coherently two spins or three spins will be simultaneously flipping. So this is multiple quantum. And one of the basic conditions for multiple quantum detection, I said all the spins should be part of the coupled spin system. Secondly, the coupling should be reflected in the NMR spectrum. For example, we looked at benzene, it has 6 protons and each proton experiences 3 different couplings. Each proton experiences ortho, meta and para couplings of different strengths, but they are not seen in the spectrum. There is no multiplicity, you get only a single peak. Similarly, we saw for ethylene or for pyrazine molecules, they are all the protons in these molecules are chemically equivalent. As a consequence, the couplings are not reflected in the NMR spectrum. So, you cannot do MQT on such systems since couplings are not getting reflected in the spectrum. That is what I said. And then we found out the barrier to the highest quantum is always nth quantum. And for any n coupled spin system, you can have n plus 1 multiple quantum, including 0 quantum. That is why it becomes n plus 1. So, that many quantum you can detect. And we also found out if n spins are simultaneously in a n coupled spin system, that is a n minus m spins are simultaneously flipping, then the remaining are passive spins or spectator spins. They indeed give rise to local field at the site of the active spins and cause a splitting. Whereas in the case of the n coupled spin system, if you go to nth quantum, there are no passive spins. There is no local field generated at the site of the active spins. As a consequence, local field is only the chemical shifts. So, the nth quantum of n coupled spins will resonate at sum of chemical shifts of all the spins. So, it will be at the sum of chemical shifts. So, this is what we understood in the last class. We will continue further today and see how chemical shift and J couplings evolve in double quantum and zero quantum excitation of weakly coupled spin 2 spin case or 3 spin case like that. So, we will continue with that today and we will start discussing evolution of chemical shift and J coupling in DQ and ZQ excitation of weakly coupled 2 spin case. Weakly coupled means it could be AX, it has to be AX in the 2X case, 2 spin case. And we have worked out the energies for the different spin states for 2 spin case, weakly coupled. Remember, in the quantum mechanical analysis of the coupled spin system, we have worked out what is the energy for alpha, 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 beta, beta, alpha and beta, beta states. These are the eigen states we got, eigen values, okay, for the energy states. Okay. So, now I wanted to show this so that we will be using this soon. Now, we will go to the double quantum in the 2 weakly coupled AX spin case. There are only 2 possibilities for double quantum we can think of. This is AX is beta beta, both AX are alpha alpha. So, the possibilities are this can go like this, alpha to beta, beta alpha, alpha to beta beta or beta beta to alpha alpha. This is the transition which is forbidden, but if we can detect it, there is only one such possibility, it is double quantum. So, 2 spin coupled case for double quantum, simultaneous flipping of beta beta to alpha alpha spin states takes place and you get only single peak, because both are active spins, super spins are 2 spins together and there is no passive spin. So, what do you get? At the they will, as I told you, both these spins flip at the sum of the chemical shifts, sum of chemical shift of A and sum of chemical shift of X. Since J couplings are not available, there is no splitting, and you get only single peak, no passive spin, no coupling. So where do the frequency of the double quantum comes? We calculate the energy for the single quantum. Now find out what is the frequency separation between the energy states alpha alpha and beta beta. This is for, and we took the difference between alpha alpha and beta beta here. Then you calculate this one, it turns out that it comes at, this will anyway get cancelled out, and this will come at sum of chemical shift of nu A plus nu X. Okay. So this is where the chemical shift double quantum comes at sum of the chemical shift of two coupled spins nu A and nu X. What happens? You may ask me a question, why are we taking the difference alpha alpha to beta beta? Why not beta beta to alpha alpha? Of course, you can take the reverse of that also. Again, it comes at the sum of the chemical shifts of two coupled spins A and X. Here also JAX gets cancelled out, okay, and then you are going to get at sum of the chemical shifts of A and sum of the chemical shifts of A and X together. So these are the two DQ transitions where alpha to beta beta and beta beta to alpha alpha takes place. That's why I showed you the energy levels and the eigenvalues which we calculated for two coupled AX spin systems when we made quantum mechanical analysis earlier. And we took simply the difference between alpha alpha to beta beta states, and we found out dq comes at sum of chemical shifts. Now let us look at the ZQ, zero quantum in two spin case. Now the same thing, it is beta alpha and alpha beta. So it is Fz equal to 0 0. This magnetic quantum number of E state is 0 0. Now both are active spins, and you can allow both of them to flip like that. Here again no passive spin. But the interesting thing is, you should remember, zero quantum comes at difference of the chemical shifts. Remember I told you, the double quantum comes at sum of the chemical shifts, zero quantum comes at difference of the chemical shifts. And no, in this case, I am sorry, this is ZQ, no, what is happening is no passive spin, no splitting is available. So JZQ is not there at all, no splitting, because it is not, there is no splitting because there is no passive spin. Okay. We will go to the next one. Now what is the frequency of ZQ transitions? We can work it out here from the energy levels which I have given you. Instead of now alpha alpha beta beta, you take the separation from alpha beta to beta alpha. This was what I gave in the table few slides before. Now it turns out ZQ is equal to nu M minus nu X. So zero quantum comes at sum of the, at difference of the chemical shifts. Now why not alpha beta beta alpha to you can also take the difference of beta alpha to alpha beta. Again you do that, you find out it is nu X minus nu A. So this is what is going to happen. See, zero quantum always comes at difference of the chemical shifts, double quantum always comes at the sum of the chemical shifts. And in the two spin case, in both the cases there is no passive spin, as a consequence there is no splitting. You get only one peak for DQ and one peak for ZQ. Okay. So this is what that's how you have to understand transitions in higher quantum. Now let us jump to multiple quantum detection in a 3 spin case. 3 weakly coupled spins will consider A, M and X. Now how many transitions you can think of? MQ. See, now highest quantum, we will look at the energy levels for this also. Single quantum transition frequencies we worked out. How many? There are 4 A transitions, 4 X transitions, 4 M transitions. We have worked out already. And we also got wave functions, and then energy of each of the states we worked out. Okay. And now we can find out from this what is the third quantum frequency, because now in this case 3 spins are coupled, all the 3 spins can flip from beta 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 to alpha 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 or vice versa. Now energy of the alpha alpha state you consider, energy of the beta 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 state you consider. Now find out what will happen for the third quantum. The third quantum, if you find out, you will see that they all come at the sum of the chemical shifts. You look at here, take the difference between this and this, then this term will cancel out, and you get only sum of nu A plus nu M plus nu X. So that's what is going to happen. Even this way again I am showing you in the third quantum case. The third quantum comes at sum of the chemical sheet of all the 3 spins which are coupled. Again no passive spin. So as a consequence there are no energy splitting, further splitting. So this is the energy difference I calculated for you already. See this is the 3Q for this one. Coming from the table which I gave you, I took the energies for the alpha 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 state and beta 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 state and took the difference. This is what I am showing you. It is coming at sum of the chemical shapes. Okay. So if you go for this is for alpha alpha to beta beta, you may ask me what happened like in the previous DQ case. If you have what happened if I take the difference, same, instead of plus here it is minus, that is all. So both are allowed transitions. It is like P equal to plus 1 and P equal to P plus 1 and P minus 1, both are possible. You can detect, select it pathway. You can say which one. Generally we always select minus 1 because that is detected. So we can here also there are 2 possibilities, alpha 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 to beta 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 and beta beta to alpha alpha alpha. So that's why we have one case where it is plus 3, other case minus 3. So now DQ transition frequencies we will see for 3 coupled case how many DQs we can think of. See, these are the possibilities. Now in the 3 coupled case of A, M and X, I can think of A and M double quantum. Means of the 3 spins A and M can be flipping simultaneously and X is a passive spin, and in each case there are 2 possible states for passive spin. When A and M is simultaneously flipping, X is a passive spin, it can be the alpha state or it can be the beta state. So there are 2 energy states for this. Similarly for A and X can be double quantum, A and X can simultaneously flip, then M is a passive spin, M can be in the alpha state, M can be in the beta state, again 2 energy states for this. There is third possibility, there could be MX double quantum where A is a passive spin. Now again it can have alpha state and beta state. So these are the energy levels for this, energy states. So now we have seen the energy differences for each of them. If you consider transitions from 1 to 7, 2 to 8, all those things, we can see DQ transition frequency. I worked it out, you do not have to take break your head. Now how do DQ comes? This is simple. AM is flipping, X is passive. So then what are how many peaks we expect? Remember 2 spins are flipping, passive spin as alpha and beta spin states. It will split this. If this is not there, this will be only giving it a single peak. Now third spin is a passive spin. As a consequence, it comes at the sum of the chemical sheets, but now we also have a J coupling. So each line, the double quantum line will split into a doublet. It split into 2 lines. The 2 lines comes because of 2 orientations, alpha and beta orientations of passive spin X. But now what is the doublet separation? Remember I have been telling you in the previous course, in this course also, always at the set of the active spin you get the coupling between the active and passive spins. Now there are 2 active spins. So you will get the coupling between AX and MX. Since they are flipping together, you get the sum of JAX plus JMX here. It is that is what is going to happen here. See now in this case, sorry. So in this case what is happening is, since this is a passive spin, you are going to get sum of JAX plus MX because simultaneously are flipping. If they were to be individually flipping, then you will get AX coupling and MX coupling and only one chemical shift. Now because of the double quantum, it comes as the sum of the chemical shifts. Okay. So now again AX can be double quantum, A and X are flipping and M is a passive spin. Then where does it come? It comes of chemical sheet of A and X. That is what happens. It comes at sum of the chemical sheet of A and X. But what is the splitting? M is a passive spin. It will split into a doublet because of JM coupling and JMX coupling. That is what happens. So double quantum of a 3 coupled case will be always a doublet, because there is one passive spin which splits this double quantum frequency into a doublet of 2 frequencies, which is the separation given by sum of the coupling between active spins and passive spins. Exactly, you can think of for AXM. Now X and M are passive spins, and X and M are active spins, A is a passive spin. So the double quantum will come at some chemical shift of M and X, and the splitting because of JAX coupling and JMX coupling. Sorry, AX. Now X and M are flipping, so it should be sum of AX and AM, not MX, AM. So this is a mistake, you please remember, this is a sum of active and passive coupling. So AX coupling and AM coupling sum, that is what happens. Okay. So these are the energy levels, you can look at it. As I said, there is a possibility beta 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 can come to alpha alpha, beta beta come to alpha alpha, both A and M spins are flipping here. This is possible. This is double quantum. And there is another state for this AM. Here alpha A and alpha A and alpha M can change to beta A and beta M. That is also possible. So for each time you have 2 possible transitions, one from here to here, other from here to here. That is the reason why you get a doublet in the double quantum, because passive spin is there in each of the case in alpha and beta states. This is what is making it split into doublet. If you look at this here, AM doublet, AM here, A and M are flipping into alpha A, alpha M will split into this is A, yeah, beta A and beta M. Okay. And similarly this will be, no, this is AX, I am sorry, this is AX. AX, alpha A, alpha X is changing to beta A and beta X here. This is AX, okay, for this one. Similarly this one AX again. Here alpha A, alpha X is changing to beta A and beta X. Now what are the other one? This is MX. Here alpha M, alpha X is changing to beta M, beta X. Similarly this one alpha M, alpha X is changing to beta M, beta X. So each double quantum has, in the 3 coupled spin case, has 2 transitions where third spin, X spin, is in its passive state. As a consequence, each double quantum becomes a doublet because of the third passive spin in alpha and beta states. So this is what it is. Now let us understand how the 0 quantum evolves in the 3 coupled spin case. Same AMX I will consider. Now remember, here alpha beta and beta alpha, their orientations are opposite here, and so it is a 0 quantum transition. Again X is a passive spin. What did I tell you? In the 0 quantum you get the difference of the chemical shifts. So you get delta A minus delta M. Similarly J couplings are also difference. Remember, one case it is JAX is positive, or it AX minus MX. Of course you can take other way also, JMX minus AX also, that is also allowed, both are possible. So in the 0 quantum the couplings evolve as the difference. In the double quantum they evolve as sums, but in the 0 quantum they evolve as a difference. Same thing you consider now AX, M is the passive spin, so the chemical shift evolves as delta A minus delta X, and separation doublet because of the passive spin is JAM minus JMX. Exactly. Now consider MX. Now MX is flipping simultaneously 0 quantum, A is the passive spin, chemical shift is sum of difference of delta M minus delta X, and J coupling is, J split doublet is, separation is JAM minus JAX. This is what it is. So very simple. Now it is, we have understood how DQ, ZQ evolves in the 2 spin case or in 3 spin case also. Again you can think of for 0 quantum it is plus half to minus half, half to half. Now 0 is, we consider A and X, AX is changing to alpha A, alpha X, alpha A beta X should be changing to beta A alpha X, or it should be this one. Okay, it is changing to beta A alpha X. You look at it, alpha beta is changing to beta alpha. This is AX 0 quantum. Similarly here, alpha A beta X is changing to beta A alpha X. This is also AX 0 quantum. Similarly, this is MX 0 quantum. Alpha M beta M is changing to beta M alpha X. This is MX 0 quantum. Similarly, this is AM 0 quantum. So all again you will have 6 possibilities here, 6 possible transition. For each double quantum there are 2 peaks for 0 quantum, because passive spin is splitting into doublet. Okay. So what are the ZQ transition frequencies? For the AMX, like DQ we saw, we can work it out for ZQ, ZQ also. AM when X is spin, what are the energy states you find out, take the difference, you will find out. For each DQ there are pair of lines at the sum of the chemical shifts equally placed on either side. That is the important thing. See, in the frequency of the ZQ, if you consider, there is a difference in the chemical shift, but on either side there is one peak which is a delta JMX, and once let us say this is a peak. Here JMX and JMX, right and left side there are two peaks, one on the right and one on the left. At the same time you also have JAX and one on the left and one on the right, but they will be coming at the difference. So these are the things which you have to understand, the frequencies of the doublets in 0 quantum. Okay. So now how do you look at it, 0 quantum and double quantum doublets? I took the simple example of the AM double quantum in AMX case. This is the alpha X and beta X. That is a passive spin in alpha and beta states. Now center of this gives rise to doublet, sum of the chemical shifts. Center of this doublet gives rise to sum of the chemical shifts, delta A and delta M, which are active spin. What is the separation giving? AX plus MX. MX is the passive spin. This is a double quantum of AM double quantum in AMX spin system. What about AM 0 quantum? Same. This is alpha and this is beta, but now it is the difference. AX minus MX is the separation. Center is delta A minus delta M. So you see the difference. This is the sum is a larger separation, and 0 quantum is the difference with a smaller separation. In both the case, AM double quantum and AM 0 quantum, X is the passive spin. So you will understand the splitting pattern and whether it is a DQ or ZQ, depending upon that you will know the separation is what is the sum of the couplings or difference of the couplings. Okay. And you may ask me a question, what happened to the coupling between A and M? They are active spins. That will not together, both of them are active, their splitting will not be reflected in the spectrum, that will not be influenced the spectrum. So now you can ask me a question. Fine, we understood DQ, ZQ, 2 spin, 3 spin, etc. Now I have an unknown n coupled spin system. N could be any number, large number, 3, 4, 5, 8, like that. How many different multiple quantums I can get in the n coupled spin system, and how many transitions I can expect in each quantum? That question we have to answer. Because double quantum of 2 spin you get only 1 peak, triple quantum of 3 spin you will get 1 spin, only 1 peak. Similarly we understood double quantum of 3 spins you will get 2 peaks for each quantum, each double quantum. So all those things we understood. Now we will understand generalization. We will generalize the formula for the different MQs of n coupled spin system, how many transitions are expected in each quantum. We will take the example of 4 spin AMPX, weakly coupled 4 spin. What is the fourth quantum? All 4 spins A, M, P and X are changing from beta, beta, beta to alpha, alpha, alpha state, like this. Okay, this is the fourth quantum. Where does it come? It comes at the sum of the chemical shifts of A, M, P and X. Done. Okay. So no local field, no J coupling, fourth quantum of 4 coupled spin is a single peak. This we understood. Now we will go to third quantum. How many possibilities are there? Third quantum is any 3 protons can simultaneously flip among the 4. Any 3 protons can flip. How many possibilities are there? There are 4 possibilities. Look at this one. These 3 can flip. X is a passive spin. Or then chemical shift of 3q is A, M and X. Some of them AM and P, and separation is sum of AX, MX and PX. That is the separation. Again it is a doublet because only one passive spin is there. Now there is a possibility AM and X can flip instead of A and P. Now P is a passive spin. So what is the chemical shift? Delta A plus delta M plus delta X, sum of all the spins which are flipping. Chemical shifts of all the 3 spins which are undergoing flipping from alpha to beta. Passive spin is P. So what is the doublet separation? JAP, JMP and JXP. Now there is a possibility APX can flip and M is a passive spin. So now 3q is delta A plus delta P plus delta X, and what is the coupling you must know by now? It is JAM, JPM and MX, all the 3 are there. Sum of them, all the 3 together will split into a doublet. Similarly now you go to AMPX. Now MPX can flip, A is a passive spin, so it comes as sum of delta M plus delta P plus delta X. And triple quantum separation is sum of AP, AM, AP and AX. That is the doublet separation. You measure the separation that correspond to this one. So now we understood triple quantum of a 4 coupled spin system. Similarly now we can go to double quantum. How many possibilities you can think of? 6 possibilities. Simultaneous flipping of any 2 protons at a time. Here we consider simultaneous flipping of any 3 protons at a time. Now we can consider of double quantum like this. 2 can flip. Now very interesting case. Where does the chemical shift come? A double quantum comes as the sum of chemical shift of A and M. These are the active spins. Now tell me, what is the J coupling? What is the separation? Separation is sum of AP plus AX and MP plus MX. Now these 2 are the active spin, there are 2 passive spins. So it should be sum of the coupling between active spins and passive spins. Now A can couple to EP, A can couple to X, similarly M can couple to P and M can couple to X. So this doublet separation is, in principle, it is not a doublet. If the couplings are different, you will get multiple. You will get in fact more peaks. We will see that if the chemical shifts, if they are not equivalent, if they are inequivalent, to so many possibilities you can think of. But nevertheless, we are going to get, if you consider a doublet, this is the sum. So separation corresponds to this sum. Similarly, this can flip simultaneously, and this is the splitting. Chemical shift is sum of A and P, and this is dq. So similarly we can have flipping of A and P and A and M and P, all those things you can think of. So there are varieties of possibilities you can think of. All 6 possibilities are there here. Please understand. Now if you come to flipping of P and X, M and X, A and P, A and M, A and X, all possibilities you can think of. You know what are the chemical shifts. They come at some of the chemical shifts, and couplings are some of the passive coupling between active spin and the passive spin, that come as a sum. Okay. So now we can give rise to a general formula for this. Number of mth quantum transition for n chemically inequivalent interacting spins. Understand my statement. Now the for any mth quantum, how many transitions we can get? If there are n coupled spins, we can get mth quantum for spin of nuclei, and that is going to be a general formula 2n factorial over n minus m factorial into n plus m factorial. That means you go to a sixth quantum. Sixth quantum of 6 coupled spins. How many peaks you expect? N is 6. It is 12 factorial 2 into n, 12 factorial, n minus m 0 factorial, n plus m 12 factorial. So, this will cancel out and 0 factorial is 1. So, you get 1. So, it is correct, right. Sixth quantum of 6 coupled spin will give only 1 peak. Similarly, you go to fifth quantum of 6 coupled spin. Here it is n into 2 is 12, 12 factorial, n minus m is 1, n plus m is 11. So, we are going to get 12 peaks. If all the two are chemically inequivalent, you are going to get 12 peaks, because there are 6 such possibilities you can think of. Each of them can be a doublet. Remember, fifth quantum of 6 coupled spins, any 5 can flip at a time. So, each time another leftover spin is a passive spin, it is split into a doublet. So, there are 6 such possibilities, 6 possible double quantum. That is why you are going to get 12 transitions. Similarly, fourth quantum, you will get, if you take it, this is 12 factorial or 2 factorial and 10 factorial, you will get 66 peaks. So, you can find out how many peaks are there for each quantum. So, if you come to single quantum, let us say, how many peaks are there? Single quantum, see, this is 2 into n 16, n is 1. So, n minus 6 minus n is, n minus small n is 5, n plus 1 7. So, you calculate, it turns out to be 792. The single quantum transitions in 6 coupled spins are 792. There are 792 transitions in a 6 coupled case for a single quantum. 6 coupled spins gives us 792 transitions theoretically. All you may not be able to detect. Some may be very weak in intensity, some has negligible intensity, that is okay. But what I am trying to say is that is the redundancy of the transitions as you go to higher and higher quantum. So, what did you understand from this exercise? As we go to higher and higher quantum, here we saw you get fewer and fewer transitions. If you go to the highest quantum, you will have only one, n minus 1 quantum few transition, and n minus 2 quantum is even fewer less transition. Only when you come to single quantum, more transitions are there. So, higher the quantum, fewer the transitions, and in a general, all I need to know is n minus 1 and n minus 2 quantum spectrum. If I can analyze that, I can get the complete spectral information. You understand? See, for example, instead of 792 lines, the spectrum I have to take and analyze 792 transitions to get this information for the 6th coupled spin case. On the other hand, I can go to this one, 4th quantum is 66 and 5th quantum is 12 lines. If I can analyze this spectrum and this spectrum, I can get complete spectral information. That my life becomes quite simple. I do not have to go to single quantum spectrum analysis at all. So, what I am trying to say is, since the time is getting up, I am going to stop here. What I wanted to say is, highest quantum gives you single peak for n coupled case. As you keep on reducing the quantum from n to n minus 1, n minus 2, n minus 3, the number of transitions keeps on increasing. If you come to single quantum, you have a lot of transitions. That means single quantum transitions are highly redundant. You do not need that many transitions to get the spectral information. And I showed here, I took the example of evolution of dq and zq in 2 coupled spins and 3 coupled spins. We saw what are the possibilities. In the 2 coupled spins case, double quantum comes at some of the chemical shifts, and there is no passive spin, so no splitting, you get only single peak. Whereas the Z0 quantum comes at difference of the chemical shifts, and yet again there is no passive spin and no splitting, it will give a single peak. We went to the third 3 spin case, third quantum gives a single peak, whereas in the 3 spins, if you go to double quantum, there are 3 possibilities. Consider AMX, there is AM double quantum, MX double quantum and A and M double quantum, all the 3 are possible. And each time Third spin, leftover spin, is a passive spin. So it will flip at some of the, both the spins will flip simultaneously to alpha and beta, but the X spin is sitting idle, passive spin. That has alpha and beta spin states. As a consequence, each double quantum of the three coupled case will be a doublet. Where does it doublet come? Come at the sum of the chemical shifts of the active spins, and the separation correspond to sum of the J coupling between the active spins and the passive spin. That is important thing. So similarly, we understood what happens if you go to the zero quantum. Zero quantum also again several possibilities are there. AM zero quantum, MX zero quantum and AX zero quantum. Each time again leftover spin is a passive spin and it splits into a doublet. And this here the doublet comes at the difference of the chemical shifts, and doublet separation pertains to difference in the couplings between active and passive spin. This is what we understood, and we even went to the extent of understanding how many peaks are possible, how many peaks one can detect in the nth quantum of n coupled spins by taking the example of 6 coupled spins. So we understand that as you go to higher and higher quantum, there are fewer transitions, you can reduce redundancy. That is the important point I wanted to tell you. So I will stop here. With this we will continue in the next class, and we will go into some few applications and try to see how we can utilize MQT and how we detect MQT and few applications. I will stop here. Thank you.